Good morning, Algebra 2. Again, this second video deals with the second part of section 14-2 on choosing among linear, quadratic, and exponential models. And I thought today in this video I'll do one example. So we're going to do problem number 4 on page 734, see how it's done. Parts of this you're not going to be responsible to do, because that's more along the line of a statistics class. But you can probably answer them as best you can by just thinking it through. So I'll let you guys do that, but I am just going to focus here on making up our equation. Okay, so here is number 4. Here, this one deals with population geography, very applicable. Once again, mathematicians and biologists, they take data like this and they make predictions, and the prediction is an equation or a function. That's what we've been dealing with for this chapter, or especially the last chapter, working with the function. And is our function give us an idea of predicting something in the future or predict something from the past? And also other questions are, is your function that we created, is that a reliable source? Is it reliable? Sometimes it can be, sometimes it can't be. Again, this is excuse me, this is something statisticians do. They take data, they make predictions, they make functions to make a prediction of what may happen in the future based upon a certain trend, whether the trend is exponentially as a decay or a growth, or it could be a parabolic trend, or it could be a linear trend. So all that stuff is really, really applicable in in our world we have. So let's look at this example, and we'll do it step by step. So here, the data set shows the percent of the U.S. population living in central cities. So again, here they've kept stats from 1910 all the way up through 1980. Once again, we don't know what state they're dealing with here, but the trend here shows that in 1910, this particular state, that 21.2% of that state's population are in central cities. Now again, that could be, doesn't mean central to right in the center of the state, but central cities may be important cities within the state. Like here in Lynchburg, we have some central cities that we are very familiar with. Roanoke is one of them. Charlottesville is another one. Lynchburg's another. Those are central cities. And what they're doing here, as the years move on, they notice that more and more percentage of the state's population are living in central cities. So like here, as an example, in 1950, 32.8% of the state's population live in central cities. So that's close to a third of the population is in a city, okay? And then also years go on, it starts decreasing. So if you look at here, we can probably get an idea of a prediction, okay? Just an idea, because like here, the first question they ask us here, what does your model predict for the percent of the population living in the central cities in 2010? Well, if we were to look at our data, we could probably say right here, how much confidence would you have in this prediction? Well, we don't know. I mean, it's so many different things we can answer. A lot of things are changing, but it varies from year to year. Job employment may take people into the big cities. Well, I'm just throwing ideas at you. Given that the actual number for 2010 was about 36.9, does this support your judgment? So in other words, what we're going to do is, they already have the data that in 2010 was about 36.9%. But what we're going to do based upon this data, that data that we found, is that going to be reasonable or is it 36.9? Is it close to it? Is it reasonable to it? That's what we're trying to do. Now, I would share this in my class. Once again, statisticians, mathematicians, actuaries, they take a lot of data like this. They're the ones that predict these functions, how they work. So again, we need to thank all your math people out there that have been gifted and taken large amounts of data, and they make some predictions. All right. So what we're going to do today is we're going to answer this question as best we can. So the first thing we're going to do is you look at your diagram. We see that our values of x are in years, and if you look at it, they're in increments of 10. So, and then we see that the percent of population is the y value. Now, I've done this already for you guys, but we notice that the first column that we're dealing with is your years are going to start in 0, and what we want to do is take and figure out what our prediction would be at 2010. All right. Now we're going to do it. Again, I'm not going to hold you responsible for physically graphing it. I want you to use your calculator. So here we go. Very simple. Take your calculator, hit Stat, Edit, and in L1 we'll do x equals 0 all the way up to 70. So all we do is plug our values in. And that takes care of, list 1. List 2 is your percent of population. Oops. Again, if you make a mistake, just back it up or clear it. All right, go all the way down the line. And 30.0. So we have entered all our data in here. So the next thing we do is we go ahead and quit this. Go to graph. Again, if at one time before you worked in your calculator, make sure now if you want to do a scatter plot, you got to make sure you have plot 1 highlighted, which in this case I already have it. Now if you look at the diagram, here's your scatter plot. There gives us a good picture of a quadratic regression. All right, so now from that data we can create our function. So go to Stat, go to Calc, and find, we already said that this is a quadratic, so now we know it's going to be a quadratic regression. So we bring it up. We don't need to worry about a lot of this other stuff. And there's your calculate. And if you look at it, again, if you go back to the diagram, once you see something, again, here it's a parabola that's going down. So that tells us that we have a negative leading coefficient. So this is a parabola that's going down. Again, I think I may have to start all over again. My fault. All right, so based upon this, we see that our function, so again, y equals negative 0.061 x squared. Again, I'm going to get as many digits in here as possible. The more numbers you have, the more accurate your answer will be. Plus 0.546x plus 20.892. So this right here is our model that we're going to deal with, or a function that will deal with it. So what we want to do is, they already told us, given that the actual number of this was 36.9, let's take from here, what does your model, which we just did here, predict the percent of population in the city in 2010. So again, 1980 is 70, so we want to go 2010, that's 30 more years, so that means our x value is going to be 100. So we take our function. Everywhere we see a x, all right, making mistakes here. Everywhere we see an x, we let it become 100. And then pull out your calculator. Do all your gazindas. This goes into that. All right, ready? Negative 0.0061 times, oops, I got to do that again. Negative 0.0061 times 100 squared plus 0.546 times 100 plus 20.892, enter, and we get a value of y equals 14.49%. Okay? Now, the next question is this. If I did everything correctly, which I probably have, let's see, I'm thinking again. This is about 15%. We got 14.5%. This right off the bat tells us pretty much that this gives us very little confidence in our model that we made. Again, like I said, this is not going to be a statistics type class. All I'm going to ask you to do is just take our information. What does your model represent here? All the second part here is just more on the line of statistics. I'm not going to really hold you guys responsible for that. Just be able to learn how to take your data and put it into the stat. Look at the function or look at your scatter plot. Think again, is it going to be linear, quadratic, or exponential? And based upon that data, I want you to be able to create your function, okay? So all that other stuff they ask you to do in there, you don't have to if you don't want to. You can go and think it through. I'm not going to worry about that. All right, guys, that's about it. I'll catch you later. Bye.